Okay, so we all hear about hydrogen, right? The clean, powerful fuel of the future. But have you ever seen what happens when you actually light it on fire? It gets weird. It doesn't burn like anything we're used to. So today, we're going to dive right into the heart of a hydrogen flame and figure out what makes it so wild.
All right, just look at this. On one side, you've got a methane flame, like from your gas stove. It's smooth, it's stable, it's kind of tame, right? But then you look at a hydrogen flame, and wow, it's a chaotic, wrinkled, absolutely wild thing. And get this, these aren't just cartoons. This is from real lab work, and it shows this deep, frankly bizarre difference in how these two fuels actually burn.
So that's the big question, isn't it? Why? How can one flame be so predictable while the other just seems to tear itself apart in this frenzy of energy? Well, the answer is this amazing puzzle, a mix of chemistry and physics. So let's start digging for that first clue.
Okay, our investigation starts with the most obvious difference, and it's a huge one. It's our first big clue, speed. I mean, the sheer velocity of a hydrogen flame, it's just off the charts compared to pretty much any other fuel we use.
Yeah. Get this, we're talking 10 times faster. 10, not 10%, 10 times faster than a methane flame. That isn't just a small bump, that is a completely different league of combustion. So this incredible speed, that's the first major piece of our puzzle. But what's actually driving it? What's under the hood?
So why is it so incredibly fast? Well, it's not just one thing. There are a few factors at play. Things like how hot it gets, how the molecules themselves move around. They all have a role. But the science is crystal clear on this. The main driver, the real secret sauce here, is all about the chemistry, what scientists call chemical kinetics. And to get that, we need to meet the tiny, tiny engines that are actually powering this whole reaction.
Okay, let me introduce you to chemical radicals. The best way to think of them? Imagine they're these tiny, hypercaffeinated particles, just absolutely desperate to react with anything they bump into. They are the essential sparks that keep the fire going, kicking off a chain reaction. And the way hydrogen uses these radicals, well, that's the whole key.
So hydrogen's chemistry, it's like a runaway engine. It's a special type of reaction called a chain branching reaction, which is basically a super powerful positive feedback loop. Here's how it works. It starts by using up just one single hydrogen radical. But then, after a super fast series of reactions, boom, that one little spark creates 3 new radicals. It literally multiplies its own firepower with every single step.
Let's think of this like a bank account for radicals. For a fuel like methane, it has to spend 2 radicals just to break down one fuel molecule. It's running at a net loss. But hydrogen, it's completely different. Its reaction actually produces a surplus of radicals. It's a system that's literally printing its own money, creating this insane feedback loop that just fuels its own incredible speed.
So when you lay it all out and tally up the score, that crazy radical-producing engine, the chemical kinetics, is the undisputed champion. It's the #1 reason for hydrogen's mind-blowing speed. The chemistry is absolutely king here. Okay, so we've solved the why so fast part of the mystery. But that still leaves the other question, right? What about the why so wrinkly part?
Right, we've nailed down the speed thing. But knowing why it's fast doesn't explain why it looks so chaotic and wrinkled. For that, we have to get into its, let's call it an unstable personality. And the crazy part is, this isn't because of wind or some outside force. No, the flame literally does this to itself.
The fancy scientific term for this is intrinsic flame instability. And all that really means is that the flame has this built-in natural tendency to get wrinkled and chaotic all on its own. And it turns out there are 2 main culprits working together to create this beautiful mess.
All right, culprit number 1 has a bit of a mouthful of a name. It's called hydrodynamic instability. But the idea behind it is pretty simple. As the flame burns, the gas gets super hot and expands fast. Think of a crowd pushing forward. That expansion pushes on the cool gas ahead of it, and that makes the flame front bulge and fold and wrinkle. It's a purely physical thing, and it actually happens in all flames. But for hydrogen, this is just the opening act.
And now for the real star of the show, thermodiffusive instability, This is hydrogen's secret weapon, and it's so cool. Let's go back to that battlefront idea. Imagine the flame front is your line of soldiers. Now the tiny, super lightweight hydrogen molecules, they're like these elite, super fast commandos. They can race to the very tips of the front line, the curved parts of any wrinkle, way faster than the heat can escape. This basically supercharges the reaction right there at the tip, which makes the wrinkle push out even more, which in turn creates, you guessed it, more wrinkles. It's this brilliant, self-reinforcing cycle of pure chaos.
So what you have are these two distinct forces working in tandem. The hydrodynamic instability, that's what creates the big, large-scale folds you'd see in pretty much any flame. But then the thermodiffusive instability kicks in, and it's the one that creates all those tiny, sharp, super reactive cellular wrinkles that are so unique to hydrogen. It's like one force creates the canvas, and the other one comes in and paints all the wild, chaotic details.
Okay, so listening to all this, you might be thinking, wow, this instability sounds like a real problem, right? Like a bug that engineers have to try and fix. But here's where it gets really fascinating. Scientists are now realizing that this chaos, it isn't a flaw at all. It's a massive opportunity. That bug is actually a feature. So how can this chaos possibly be a feature? Well, by wrinkling itself up like that, the flame does something absolutely incredible. It massively, and I mean massively, increases its own surface area. I mean, think about it. A crumpled up piece of paper has way more surface to work with than a flat one, right? It's the same idea here. More surface area means way more space for the fuel and air to mix and react. The chaos itself is what allows the flame to burn even faster and more intensely.
And the real-world consequences of this are just huge. All those wrinkles, those cellular structures, those little finger-like folds, they combine to completely supercharge the combustion process. What that means in practice is you can burn more fuel way faster and in a much smaller space. For engineers trying to build the next generation of engines, this is an absolute game changer. It unlocks the potential for designs that are way more compact, more powerful, and a whole lot more efficient, whether we're talking about jet engines or power plants.
And look, you don't have to take my word for it. The scientists who are deep in this research, they put it perfectly. They say that these instabilities, they bear a huge potential to be exploited. So this isn't just some neat theory. This is the absolute cutting edge of combustion science, and it's all about figuring out how to turn this chaos into a major advantage. So, let's bring it all home. What does all of this mean for the future of energy? Well, we've seen that hydrogen's wild, chaotic fire isn't random at all. It's a direct product of its unique chemistry and this incredible built-in talent for self-enhancement. And realizing that, well, it changes absolutely everything about how we should approach using it. This discovery forces a fundamental shift in our thinking. For decades, the goal for engineers was always to make flames as stable and smooth as possible. But with hydrogen, we now know that's completely the wrong goal. The real key to unlocking its incredible potential isn't to fight its chaotic nature, it's to harness it. To design engines that are built from the ground up to take advantage of this beautiful, powerful instability. So in the end, the biggest challenge of our hydrogen future isn't just about figuring out how to make the fuel, it's about learning how to build the machines that can work with its beautiful, chaotic, and unbelievably powerful fire. The goal isn't to control the chaos, it's to become its conductor. Thanks for digging into this with us.